And we saw yesterday that the indeterminate form of a limit was when it's either 0 over 0 or infinity over infinity. So when we look at this, this is one that we did early on. If you look at it and you plugged in 2, you would get 0 over 0. But this is one we could have done before because you could have factored it, and after it simplified, it became x plus 2. Okay? This is dangerous. I always say if you're going to do math to check it, put it in brackets. Write indeterminate form, because if you ever write that the limit is equal to 0 over 0, it's automatic deduction on the exam. Because it's not. It's equal to 4. It's not equal to 0 over 0. This limit is equal to 4. The part of the process of discovering that was to take the derivative first. Now, you could have solved this one with factoring. We're going to learn that we can now apply L'Hopital's. Where does the hat go on that one? I don't know. That's fine. I like hats. And if I did apply L'Hopital's, this would become 2x over 1. Can I do the limit now? This is one I could plug in. I get 4 that way as well. So that's really cool that we can now do this same question with L'Hopital's rule. Especially when I give you one like this. Do you remember the old technique? Oh, maybe I should have had x cubed minus 8 on the bottom. Right? But this one, oh, I feel like doing this in a different way. If it had x cubed minus 8, you'd have to remember how to factor a difference of cubes. Which some of you are looking at me and going, yeah, I forgot that. Okay? But now you can use L'Hopital's rule. But if we look at this one, it is infinity on the top, infinity on the bottom, but the bottom is stronger. And so whenever your power is bigger in your denominator for a limit, it's going to go to 0. If we did L'Hopital's rule, eventually you would get just an x on the bottom and a number on the top. And the limit as x goes to infinity of 1 over x is equal to 0. Okay. So these are some review ones that we've done before. And this is a review one. We talked about it yesterday. We used to have this memorized to be 1. Okay? But now it is an indeterminate form. Put that in brackets. And so L'Hopital's rule is going to tell us, and so when you're doing this on your test, you write out that it's indeterminate form. That allows you to use L'Hopital's rule. You can't use L'Hopital's rule in any other case other than 0 over 0 or infinity over infinity. And once we apply L'Hopital's rule to here, derivative of the top is cosec, derivative of the bottom is 1, and now I can plug in 0 and get 1. So that's L'Hopital's rule. If you have the indeterminate form, 0 over 0 or infinity over infinity, then the limit as x goes to c of the derivative of the top over the derivative of the bottom is the same as the original limit. And sometimes you have to apply L'Hopital's rule many times. So we just did this one. Okay, again, first of all, put this in brackets. State that you have the indeterminate form. If you just apply L'Hopital's rule before you state that, you may lose a mark because you haven't checked whether you're allowed to use it. They're very stuff like if you don't state something's continuous, you can't use the intermediate value theorem or the mean value theorem when we get to that one. Or the extreme value theorem. There's three IVT, MVT, EVTs that we're going to have. So it's very important that we state this. Okay? Put this in brackets. On the video that we watched on AP Classroom, they were very formal in that they did the limit of the top, they did the limit of the bottom. This is enough. You can be more formal if you want. But it's just important that you never, like, this would be bad. Here, I'll write it in red. As soon as you do that, it's not equal to 0, 0. It's equal to something. So, we take the limit. Oh, I erased a bunch of stuff. The derivative of the top is negative 2 sine x plus 5. The derivative of the bottom is 4. Now I can plug in 0. And I get just 5 over 4. Let's do 2 more together, and then I'll let you try. The rest, I'll put up the answers as we go. Put this in brackets. We plug in 0, we end up getting 0 over 0. Indeterminate form. So that means we can use L'Hopital's rule. Do the derivative of the top, the derivative of the bottom. When you go to plug things in, put brackets again. I'm sad because I got the indeterminate form again. But don't give up. Just keep deriving. I do the derivative again. And this time when I plug in 0, I get 2 over 16. And I've got a limit. So L'Hopital's rule to use, actually quite easy. What do we have to know? We have to know our derivatives, which we should. And we just have to know when we're allowed to use it. So you get a limit question that you have trouble with. Check if it's the indeterminate form. This now makes a bunch of the limits that we did in our limits unit easier to do. You had 2 methods that you used before. Remember the factoring was one. If you could cancel out the factor, then you could solve it. Then there was multiplying by the conjugate. Remember that method? Right? It might be that all of that is way easier now with L'Hopital's rule. You could write infinity over infinity and say indeterminate form in brackets, right? It is assumed that you know the end behavior of all of the graphs that you have. So you know the end behavior of natural log, right? Here's your natural log graph. Do you see that it is going up? Oops. Right, here's our natural log graph. Has an asymptote here, but it keeps getting bigger and bigger and bigger. So as x goes to infinity, the y values get bigger and bigger and bigger, and so you know that the natural log of infinity goes to infinity. But the question was, do I have to prove that with a graph or with something? No. Okay, so you can write infinity over infinity, which means if you're like, I don't really know, but I hope it works, and you wrote infinity over infinity and it worked, you'd be okay. Which allows me to take the derivative of the top and the bottom. And if I simplify this expression, it just becomes 2 over root x. And if the bottom gets really big, your limit is 0. So here, it's actually undefined over undefined. We take the derivative. And you get 1. So another, I guess we didn't really talk about it. Another version of L'Hopital's is if the top and the bottom are both undefined, they're both sort of approaching infinity in this situation. Okay, I'll show you the answer for the next one. It is the indeterminate form. Do the derivative. Here I would lose marks. Okay. I would have to write this. But if I wrote it just the way that I had there, I would lose marks for writing it incorrectly. Indeterminate form twice, take the derivative again. And this time I get infinity over 2. Okay? So we can kind of, like, these would probably show up as shortcuts. And if you did this just in your head on a multiple choice, that would be fun. How did I do that? Well, I know the derivative of e to the x will always be e to the x. It'll never go away, no matter how many derivatives I do. If this was an x to the 20 on the bottom, you would have to use L'Hopital's rule 20 times before you got an answer. But eventually x to the 20, after multiple derivatives, will go to a constant. And then you'll get infinity. So with derivatives that go to infinity, sort of a hand-waving way of figuring them out mentally is you have to decide what's more powerful. And an exponential function increases way faster than a squared function, or any polynomial function. And so you could always do that as a shortcut to get infinity in this case. Especially nice on multiple choice. On these last ones, plugging things in to check. I'll put this in brackets. It's the indeterminate form. That allows me to use L'Hopital's. And this is 1 over 1, which is 1. For me, there's something, I don't know, satisfying when the limit's a number. Like, when it's 0 or infinity, it's kind of like, oh, disappointing. But it was like 5 over 13. I'm like, ooh. Right. Sometimes we have to be careful. Okay? This is like infinity times 0, the way that it's written right now. Okay? That's not indeterminate form. Indeterminate form is when you have 0 over 0. However, if I take this limit, I know that the top part is 0. And instead, I write the x that's in the top on the bottom as 1 over x. Now, if I write it like this, now it's in indeterminate form of 0 over 0. So sometimes we have to take our equation and rearrange it so it fits the indeterminate form. Once it's been rearranged, now you can take the derivative of the top and the derivative of the bottom with L'Hopital's. Ooh, secant squared. Chain rule. And look how nice this is. That cancels out so nicely. Well, as x goes to infinity, 1 over x goes to 0, and secant squared of 0 is equal to 1. This is a tricky L'Hopital's because you had to rearrange your equation to make it fit L'Hopital's rule. Because 0 times infinity isn't L'Hopital's rule. Well, technically it is because you can almost always switch it to 0 over 0. But, and the last one. Uh-oh. It's not a 0 over 0. The top would be 1, the bottom would be 0. So the question is it infinity? Or is this a mistake? Because the issue I have with the 0 on the bottom is if it's a positive 0, it's definitely infinity. If it's a negative 0, then it would be definitely negative infinity. Okay? So I'm going to just, I wrote that out to begin. I can first say it's not the indeterminate form, in brackets here, but I should really check is as I approach 0 from the positive side of e to the x over x, the top is positive, the bottom is positive, this is going to be infinity. And as I approach the limit as x goes to 0 from the negative side, the top is still positive, but now my bottom would be a small negative number. So actually, the answer to this one is that it does not exist. If this was a multiple choice question on your AP exam, you know that one of the answers is going to be infinity. One of the answers is negative infinity. One of the answers is does not exist. Well, they'll probably put 0 in there because it's like, what's also most likely? And then, okay, what are they looking for? The people that use L'Hopital's, you'll get infinity. You'll get 1. Sorry. If you use L'Hopital's on this one, you'd get 1. Oh, they put that as an answer too then. So, careful. When we can use L'Hopital's, when we can't. This one we can't. This one does not exist. And we're done the unit.